So yeah, this week will be really about shortest path, and like it's such a fundamental topics that has been developed for like almost half a century, and still really exciting new still happening like this year or last year. But you might have seen like what shortest path algorithm have you seen before in previous class?
Like Floyd-Warshall.
Floyd-Warshall, okay. Any more?
Dijkstra.
Dijkstra, okay. That's the two algorithm that you have seen. Have they taught you Bellman-Ford before? Bellman-Ford too. Okay, cool. So like today I still gonna like talk about what you might have seen, just to brush up like what you have seen. And next class we're gonna talk also about like shortest path in dynamic graph. Like what will happen? Can you still compute shortest path when the graph keeps changing? Like that's kind of a new topic. But today maybe like old stuff. But so if you didn't see it before, then that's good for you because it's really fundamental thing. If you have seen it before, then like just a reminder, right? Yeah. Okay. So okay, shortest path. For this problem, like you have a graph, a directed graph like this, right? Like each edge has some direction, and let's say it has n vertices and m edges. I will use m and n like throughout this lecture, m for edges, right? And each edge has some length, okay? Like here. The length can be negative. It might not be positive like this. Okay. And now when you have a path pi, like the red path here, then the length of the path is just like the total length of all edges inside it. Like here it's just like 5 plus 1 plus 3. So that's 9. Okay. And now when you ask about this distance from S to T, which I denote by this from S to T in G, distance from S to T is just like the shortest length of any ST path. Okay, that's the
And are we saying that you can only include each edge once so that negative weight edges don't just get like taken infinitely?
So good. You can actually show that if there is no negative cycle, then every edge will be used once actually in the past. Like there's no point to use two edge twice, like one edge twice, because suppose that this is a path and actually it reuse this edge. So this is like a cycle, and if there is no negative cycle, then you could just like instead of look through this thing, just remove this part and go directly here. So yeah, in the shortest path, like you would not use one edge twice anyway. But if there is a negative cycle, then yeah, then you might look through things, and usually we want to avoid this scenario. Okay, right. So yeah, like this is related to your question. Okay, distance from S to T is like an intuitive, but there are actually two reasons that it's not well defined. That is, there is actually no shortest path from S to T. Can you tell me what are the two reasons?
One could be if they're not connected by the edge, so they're like two disjoint graphs.
Right, like there is no path at all from S to T. Then like it's like distance is like infinite. Right? How about another one?
Or there's a negative cycle.
Right. If there is a negative cycle, then like you might loop through the negative cycle again and again and keep reducing the distance. So it's like this time it's like negative infinite. Okay. So that's the two reasons. Like either like there is no directed path from S to T at all, or there is a negative cycle between a path from S to T. Okay. So, but assume that this doesn't exist, then the distance is well defined. And like there are really kind of two versions of shortest path problem. And for now, in today's class, we will actually focus on just computing the number, the distance. So there are two versions. One is called single source shortest path. That is, you fix the source S, and you want to compute the distance from S to every node T. That's like single source. Otherwise, there is another version called all pairs shortest path. So here you want to compute distance from S to T for all pairs S to T. Okay. And yeah, these two versions, we just want to compute the number for each node or for each pair. But there will be exercise that like once you know the distance, the number, you can actually recover the path from S to T easily, or the path, like the shortest path easily. So for today, just let's say focus on the distance. Okay. And the first algorithm that we will see is Bellman-Ford algorithm. Okay. So in this problem, okay, we have n node m edges again, and let's say I assume that there is no negative weight cycle. We will at the end remove this assumption, and I will show an algorithm that have this running time mn. Okay, and you will see that like most of the shortest path algorithm, when you reflect upon it, it's just dynamic programming when you do it on a graph. Okay, like there can be exponentially many paths from S to T, and yet you can still compute the shortest path in polynomial time by kind of remembering some information and don't like recompute things again and again. Like it's really dynamic programming. Okay. And so in Bellman-Ford algorithm, there is one key definition, and that definition is I-hop distance. So I denote it by this I-st. Okay. So this is like the shortest length of an st path that use exactly I edges. And we can also define like at most I hop distance, which is the same thing except that now I allow at most I edges. Okay. So let's see. So you can see that like the I hop distance or at most I hop distance is always at least the distance itself, because it's like you add more restriction. You look at only like a subset of path that is like have I or at most I hops. So but distance itself have no restriction. But okay, so this is at least the distance. But it could be the case that the at most I hop distance is just like incredibly much larger than the real distance. That can happen. Can you or anyone like give me some example when like this can happen? Let's say I is 2.
If there's like 2 edges that are 1,000 weight, and then 3 edges that are like 1 weight, and you have to take the 2 edges that are 1,000 weight instead of like going around and taking the 3 edges.
Good. Let's say like this is like a S and T, and like there are 2 edges you said with weight like 1,000, and then maybe like a 3 edge here with weight 1. Okay. And okay, the shortest path is obviously this one, but this use like 3 edges. So if you are allowed to use at most 2 edges, then you need to go through this, which is far worse. Okay. But okay, So when I is small, then you like it might be not like a good distance. But I want to ask, okay, what I like? Can you choose like this I, such that you can ensure that this thing is exactly the real distance?
The number of edges in the graph.
Number of edges would be enough. Why is that?
Because there cannot exist a path, unless there's a negative weight cycle, but there can't exist a path that uses one edge more than once.
Yeah.
Otherwise it wouldn't be optimal. Or like, at least there exists one that uses it that's optimal.
Right.
And so, yeah.
Right, like a path, kind of, like you can assume that if there is no negative weight cycle, then each path use each edge at most once. So like a path will use at most m edges. So that's true. Can you get even better bound?
The vertex is -1 because like you're never gonna, assuming there's no negative cycles, which I mean would make everything would all bets would be off, but you would never visit any vertex more than once anyways.
Right. Good. So here you should so you said n-1, and usually like so maybe when I equals n-1, and usually when we usually assume that m is at most m, because otherwise the graph is not even connected. Yeah. So this bound is better than this bound, and that's true. So let's see why is that. Okay. So this is like a simple lemma saying that if there is no negative length cycle, then this is true. Like the n-1 at most hop distance is just the real distance. And the reason is like kind of in like from this picture. So suppose that it's like a shortest path that use like more than at least n hops. If it use at least n hop, like at least n edges, then it must hit n+1 nodes. Right? If it use 1 hop, then it use 2 nodes. If it use 3 hop, then it use if it has 3 hops, then it use 4 nodes. So if it use n hops at least, then it use n+1 nodes. If this happens, then it means what? By pigeonhole principle, you must hit like some node twice, which is like this cycle. So it must hit some node twice. So it must contain a cycle like this cycle. Okay. But this cycle is not negative. So you could just remove it, and it will not increase your length. So now you reduce the number of hops. So you can keep reducing the number of hops until like it's at most n-1. Make sense? Yeah. All right. So now we know that, okay, suppose that there is no negative length cycle, then your goal is just to compute this one. Like this distance from S to T, when we just focus on like n-1 hop at most. Okay. So with this in mind, if you wanna try to solve this, like, and again, like we're gonna use our approach of dynamic programming, that is try to get some recursive formulation. That's the starting point. So how do we hope to compute this thing recursively? Okay. So okay. So you can try to think. Suppose that I want to compute, let's say, distance from S to some node V using exactly I hop. Okay. How can I compute this? Given that maybe I have compute like in a recursive way by looking at the distance from S to other stuff using I-1 hop.
Well, if the other thing is a node that has an edge pointing to V, then you would take the minimum of all those, the minimum of all those distances, and each distance you would add that with the weight of the edge pointing to V.
Right, right. Okay, very nice. Yeah, thanks, Guy. So, so basically you said that, okay, the distance to V, like, you will have, to go, like the shortest path from S to V must go through some of the in neighbor of V. So maybe it's go through this guy, right? And what would be the length of this path? Suppose this is like a shortest path, P star. The length of this shortest path is going to be the length of this edge from U2 to V. And the length from S to U2. Okay? Like if this is the shortest path from U to V, then the subpath here from S to U2 must be shortest path from S to U2 as well. So this is gonna like the length here is gonna be distance from S to U2. And it's gonna use exactly I-1 hop. Okay. If this is the shortest path that use exactly I hop. Okay. So this is like the type, like the form of, like the format of the I hop distance. It use some shortest path that use exactly I-1 plus the length of this guy. You don't know which one, so you just try to minimize through all of in neighbors. And you get this. So this is an I hop distance. It's just minimizing overall neighbor of V, in neighbor of V, U. Yeah. And the distance I-1 hop distance from S to U plus the length of from U to V. Okay. So that's the formula. Like that's the recursive formula. Okay. So why is that? Well, yeah. I guess I explained that. Okay, you have the recursive formulation now. Can you now, like if you want to do dynamic programming, the next thing you kind of want to check, like for computing your running time might be, okay, how many subproblems are there to compute in this recursive formula? How many possible subproblems?
N squared.
N squared. Why is that?
Up to n, an order of n, like measurements of distance, like for I, and then the destination. There are n other nodes.
Yeah.
Yeah.
Good. Like, not that like you kind of just need to look at the parameter of these things, right? Now S is fixed. It doesn't matter. Now I is just a number from 1 to n. V can be, there can be n vertices. So this is like n square, many possible subproblems you look at. Make sense? Questions? Okay. So yeah, now okay, you kind of think, okay, the running time should be something like similar to n squared now. But okay. But that would be true if like this formula takes just constant time. But it's not really the case. But we need to be a bit more careful when thinking about running time. But anyway, we have recursive formulation. So now just try to fill in table bottom up. Okay. So okay. So you just start with like initialize your table. Here, this indexed by int. This here is like a memo from previous lectures, right? And you start with this base case, saying that like the distance from S to S using like a no hop, it's just 0. And then you look at like range from I equals 1 to n minus 1. And now you try to fill in, like for each node, you try to fill in this thing, okay? This is gonna be just your formula here. Okay, so let's try to analyze the running time more carefully. Well, here there are n loops here because that's the possible number of i's. But the loop here actually takes more than n time. Right, there are n loops, but the time that you spend for like each vertex is not constant. It's really the degree of a node V. Okay. But now you sum over all node V. That's like number of edges. Sum of degree is like a m or 2m if the graph is undirected. So this is m. This is n loops. So the total running time is mn. And at the end, okay, you have computed exactly I hop distance for all I to every node V. So you need to return distance at most n minus 1 hop from S to every one. So that like just take a minimum of this thing.
Yeah. So we get the big O of M term from the length from U to V, correct? In the recursion. On average, wouldn't there be wouldn't there be less than M edges going into any given vertex?
Oh, no. Like, so M here, like in each of this thing, we just spend not M. We just spend order of degree of V time.
Okay.
Yeah. So now I sum up over all vertices here, so I get this sum over nodes.
Oh, I see. Okay.
Yeah. So this whole loop here spend in total M time.
Okay.
Yeah. Okay. So the running time at the end is OMN. So that's Bellman-Ford. All right. Okay. So now let's try to handle like the assumption that we have from the beginning. What if there is a negative length cycle? So, okay, so now the problem might be, okay, if there is no negative length cycle, still compute shortest path, like single source distance, like for all t here. But if there is a negative length cycle, then like report that. Okay, we don't assume anything anymore. Okay, so how do we do this? Well, the simple observation is this. Suppose that a node V is in some negative length cycle. Then I claim that if you compare distance at most n hop from S to V and distance at most 2n hop from S to V, then like this guy will be strictly less than this guy. Why is that?
Because the at most 2n would necessarily take the negative weight cycle. And it is necessarily allowed to do that because it can at least take the negative cycle one time because it's 2n.
Very good, very good. Yeah, like this distance at most n hop, distance from S to V can look like anything anyway, like it's from S to V. But if V is in another negative length cycle, then you could always like, this is negative, yeah, negative. You could always like take another loop through the cycle and get smaller distance. So like you can always improve like the total weight just by looping through the negative length cycle here and get less total length compared to this one. Right. And okay, with this observation, that's good. Actually, you can get something stronger, but I let you think about this as an exercise. Like you don't need to go to 2n. It's just like a at most n. That's enough. At least for some v, this must happen. Okay, but exercise if you want something fun to think about. Anyway, back to this guy. Okay. With this observation, what should we do to detect a negative length cycle in our pseudocode maybe? How should we modify our algorithm?
If when we like recompute the distance from S to V for a greater n, if it's greater, then we just output, oh, there's a negative length cycle, basically.
Yeah, like we can really literally just like check this in the code. Yeah. Just instead of like looping, like we used to compute the distance at most n-1 hop. Now let's say like we loop for I up to 2n. Increase the number of loop a bit, but still the same order, and then just put this put this condition at the end, right? So okay, so the change is just loop for I up to 2n. Everything here is the same, but now at the end you check this thing. And if it's the case, then report negative cycle. Make sense? Okay. All right, so that's good. So that's like a nice and simple, and it has been discovered by Bellman like 70 years almost ago. Bellman, by the way, is the one who really kind of invented this concept of dynamic programming. He's like the guy who do this kind of research, and there's some story about him, like why we call dynamic programming. But yeah, it's a fun story. I will not go into it. By the way, like there is some exciting news. Like people have been trying to improve this algorithm for a super long time, actually, and it turns out that no one have any progress until last year. Like we finally get improvement. It's not a big improvement, but it's like at least the barrier is broken. Now it's not mn, it's m to the m times something less than n. And then like this year, it's now improved again. So I don't know when it will stop, but like so we'll see. Yeah. So this is super exciting, and the algorithm is not so crazy. Like you can even have a look. This is like the link I put there. Okay. Okay, so that's nice, but there is even more. Like there is really another fantastic work which shows this. You can actually get something like m near linear when you assume that like the weights or the length are integer between, like let's say minus w and w, and usually you think of this w as like let's say n cubed or some polynomial in n. If you think of that, then log w is just like log n. So that's really fast now, and this is kind of a reasonable assumption, right? Like a weight are integer, which is not too big, not too crazy big. Okay, and this is actually even before this work, yeah. And the idea are completely different.
Sorry, what's the STOC paper or FOC? What does that mean?
Which second?
Like best STOC paper.
Oh, Stock is the name of the conference.
Oh.
Like Stock is like a symposium of theory of computation. and this is like foundation of CS. Like Fox and Stock are the best TCS conference. That's like there are two of them. The Fox, Stock, and then like another one that is really good too is Soda. Soda is like a focus on algorithms, but Fox Stock really like everything, like anything theory. Yeah. So that they both get the best paper. Okay. And if you want to read about this, there are even like a simple, like short paper explaining this paper. And you can have a look. All right. So really nice, like nice news. Yeah. Okay, good. So next thing I want to talk about is all pair shortest path algorithms. Okay. Now new problem, like we want to compute the distance between all pairs. And if you want to do this, like one option is just to run Bellman-Ford from every source. That will give you all pairs. But the running time would be, okay, mn for one Bellman-Ford and do it for n times. So that's like mn square. That's not nice. That's a bit slow. So we want to do better. And so here's a better idea. So what Bellman-Ford, like the recursive strategy of Bellman-Ford, you see that like we try to compute this guy, like I hop distance, using I minus 1 hop distance. Okay, now the new idea is this. Can I actually compute like at most I hop distance based on like at most I over 2 hop distance? So if this is the case, if I can do this, you see that like the recursion, like the loop in the recursion is like better, right? We base like here like we base ourselves on just something like I minus 1. And here we base ourselves on like I over 2, so like we can make progress fast. Okay. That's the hope. Like we want to get, like suppose that we have computed all pair distance between any pairs of that use at most I over 2 hops. Can we try to compute this one? That's the new idea. Okay. So, any ideas how can we do this?
If you consider nodes in between as like candidates, so if there's like a node like W in between S and V, that would be the distance from S to W and then W to V, where their i's, they're being summed to I or whatever.
Yeah, good. So you think like the distance, like the path that use I hop here, at most I hop from S to V, this path, there must be like a middle guy on the path. And this middle guy, like a distance from the middle guy to S, it use like I over 2 hops. And from the middle guy to V, use I over 2 hops. So if you have like information about I over 2 hops distance, then we should be able to compute this guy. And we don't know who is the middle guy, so we can like guess and loop through all of them. Okay. So yeah, that's the idea. So okay, like if you have S here and V here, if this use at most I hops, right? There must be like one node in the middle, like X, such that this path here use I over 2 hops, and this path here use half of I over 2 hops. That's the key idea. That is, each path must have a middle node. All right. So now, yeah, can you tell me what should be like with this idea? Can you now really give me the formal recurrence of how to write this thing based on this thing? Yep.
So you would try every single middle node and you would take the minimum length of the sum of both of them together.
Good. Minimum over x, the middle node, and the sum of distance from s to x, right? And the distance from x to v, and this will be like at most I over 2. And this is what we want to compute. That's what you mean, right? Good. Yeah, exactly. And yeah, that's our recursive formulation. We have it. And okay, I write down for you too. And okay. So this looks really nice. Like we base like to compute like at most I hop here. You can like compute something like start from I over 2. This is like a nice progress. A quick question. Why can't we use this idea like when you use when we try to do single source shortest path?
It's because we're recursing on 2 different sources, right? We have S as a source and then X as a source.
Exactly.
In a single source, we're not computing X as a source.
Yeah, thank you. Yeah. Here we like the formulation here is based on this guy. Like we need like X as a source. So it doesn't work. But it works if we try to compute all pairs, shortest path. We have prepare all of this. Okay. Good. All right. So now what we can do is like, okay, we have formulation. Let's fill in table. Do it bottom up again. So, okay. How many sub-problems are there again? In here?
Did n cubed now because I ranges from 1 to n, or like O n, and then same thing for both vertexes.
Good. So you said like S, there are n choice for S, n choice for T, and n choice for I. So that's n cubed. Okay. I claim that we can actually do better. Because not that, like can we do something about this better?
Be n squared log n because we're like halving I over and over again, or I guess doubling I over and over again.
Yeah, we just kind of doubling I, start from like up to n. So actually like the choice of I here can just start from 1, 2, 4, 8 until like something power of 2 that is more than n. So that's like log n minus choice for I. Right? So the number of subproblems we have is actually n squared times log n. That's the point of like trying to get like a path doubling. We reduce the number of subproblems here. Yeah. Not n, but log n. Okay, so now we try to, okay, we have the subproblem for all for I, S, and T. Okay, and so we're gonna like fill in some of the base case here, which is like the base case is when you use at most 1 hop, and this is like a kind of something trivial you can fill in. I will not go through this, and okay. And note that now I just need to try to compute like distance that use at most 2 to the I hops, ranging from when I range from 1 to log n. And try to do this for every s and t. Okay. And how to compute this? Just use our recursive formula. Okay. What's our total running time?
Is it still n squared log n?
So yeah, it's gonna be a bit more actually. N cubed log n. Why?
All nodes S, all nodes T, all nodes in between S and T, or should be all nodes, and then also log n.
Yeah.
Yeah.
Like it's like log n factor here, n square factor here because we loop through all pairs here. But to compute just this cell, we need to loop through all x. So log n here, log square here, and like log like n factor here. So in total, like multiply them up, you get log cube, like n cubed times log n. Okay. And at the end, you just return this thing for all pairs. Yeah. Okay. So good. So that's like how to one way to compute all pair shortest path. Okay. All right. And we're gonna see another algorithm, which is something that some of you have seen, Floyd-Warshall, right? So the path doubling idea that is kind of similar to Bellman-Ford algorithm use this much time, but Floyd-Warshall gives you a bit better. It's gonna be n cubed time. Okay, no log n factor. Okay, so the idea is this. Suppose that, okay, you have vertex set V. Let's say we order them, right? Give them name V1 up to Vn. And now, let me define what is intermediate vertices of a path. So let's say that a path starts from S, end at T, and then it goes through this guy, right? Then this, like inner vertices here, I call it intermediate vertices. Inner vertices or intermediate vertices of this path. And now there is like a really key definition for Floyd-Warshall. Let me call it like a distance from S to T, bracket I. Use different notation. This is just like a distance from S to T such that I try to restrict the inner vertices to be from some set. Okay, so this will denote the shortest length of ST path such that the inner vertices can only be from this set. Can only be from like the first I nodes. It might not use all of them, but cannot use like an I plus 1 node. The I plus 1 guy also, and so on. Okay. So let me give you example. Okay, distance from S to T when I is 0. So that this means like you don't allow any inner vertices. So in this case, it's going to be 100 because this is a path with no inner vertex. What about this one? I'm allowed to use like V1 up to V4. Then the shortest path of this type is going to be this one because I cannot use V5. I can use V1. And if I allow like inner vertices to be up to V5, then like I actually can go through this one. And that's better. Okay, so that's the definition. Okay, so question about the definition. Okay, so now claim that the final goal is then just to compute distance from S to T bracket N. And this is just gonna be the same as distance from S to T, because now here it's just really there is no restriction here. We allow the inner vertices to be anyone. So it's just the same as distance. So that's the goal. And with this formulation here, this kind of lends itself to a recursive formulation. So the strategy is like, okay, suppose that we want to compute distance from S to T bracket K. Can we try to do this based on all pair distance bracket K minus 1? Okay. So we need to think of recursive strategy. And okay, the key idea is that suppose that we have a path from S to T, a shortest path from S to T that have inner vertices from suppose inner vertices can be from V1 up to Vk, right? There is two choices here. Either either this path will use Vk as inner vertex, or it will not use Vk as inner vertex. So otherwise it's gonna be blue one here, go through only V1 up to Vk minus 1. That's the two choice. Either use Vk or not. Okay. So with this key idea, tell me what should be the recursive formulation for this one.
Be min of going through Vk or not, which would be so the min of dist with K minus 1, I think. So that's just you're not using K.
Right. K minus 1.
And then the other option would be to add K, which would be, I guess, for all edges, you consider replacing them with an edge to K. I'm not exactly sure how
Yeah.
to formalize that.
Not clear what you said here. Anyone this is the case that not use K, not use Vk. Anyone has a suggestion for another case here? How should it look like?
Split up the two different terms. One that goes to K plus S to K
S to Vk.
plus
And what is this here?
divided by 2, the number of edges.
Divided by 2?
It's not K, it's K divided by 2.
Okay, let's see. But you kind of said
Vk to T.
Vk to T. And okay. So what should be in here?
Are we going to try everything that sums to K or not?
I think it should still be K minus 1, right? Because we're using all the same vertices that we were using in the other case.
Yeah. So the correct answer is actually just K minus 1 in both of these. Why is that? Because look at this path. This is just a path from S to Vk such that it uses inner vertices from this guy. It can use anyone here, really. And from Vk to this guy, it will use anyone here up to Vk minus 1. Okay, so if you put something like K over 2, that's it will not reflect this this idea. So you put k minus 1 here, k minus 1 here. Okay. Good. So that's the correct recurrent. And how many subproblems are there here? That should be not hard. N cube, right?
Yeah.
Range from k, which is k can be 1 up to n. S and t, there are n choice for them. That's n cube. So that's more number of subproblem than the previous idea. But how fast can you compute this one? Given that you have this, and this, how fast can you compute? Can you compute this guy? O1. Now it's just kind of do some one addition and take min. That's O1. We used to pay a ON in the previous idea, but here it's just O1. Okay, so with this, we are kind of done. Try to write up some table, put the base case, fill in the table, and range from 1 to n, loop through our vertices and put in our formulation. And there are ON here, ON square here. Each of these takes O1. So in total, that takes n cube operation. Okay.
Yeah, and what is k again? Sorry, I think I kind of got confused.
What is k?
Yeah.
K is the parameter such that maybe put k is I here. Yeah. So distance from S to T bracket I is the distance such that we allow to use only the first I vertices as inner vertices.
Okay. Yeah.
Does it matter at all how we label the vertices? Or
Not really, no. Yeah. We can take any order. Yeah. But it must be consistent throughout the whole algorithm. But fix the order first, and any order would be fine. Okay. Question about this algorithm? Floyd-Warshall. Okay, good. So what's about okay, so this is a n cube time. What's the best known algorithm? So it turns out that the state of the art is quite worse. So it turns out that we can actually show some evidence that we don't expect faster than n cube algorithm. At least it's a really big open problem. So there is nothing better than no running time better than n cube is known, and this is one of the biggest 3 open problem in algorithm. APSP is one of them. Another 2 problem I can define it if you want, but yeah, you can look it up too. But the thing about APSP, our patches path, is kind of really nice because it's playing a similar role NP completeness theory. So you have seen that any problem that is NP complete, if you can find a polytime algorithm for just this single problem, then 1,000 other problems, you will get polytime algorithm for 1,000 other problems. Now, APSP plays similar role, but in a polynomial time regime, where it turns out that we can prove that if there actually exists better than n cube running time for APSP, then not 1,000 but more than 10 other problems, you're gonna simultaneously get faster than n cube running time too. So this is kind of a central problem among like a polynomial time regime. So this is like a really interesting theory. Again, this is like from fine-grained complexity. If you want to learn more, there are like some online courses, or at some point we're gonna offer them. I don't know when. Yeah. But okay, we don't know this kind of running time. But what's known is this kind of running time. Some weird improvement. What is this? So this is like this thing, 2 to the square root log n. This is actually still like much bigger than n to the 3 when this is worse than polynomial improvement if this is a constant, because this is like actually less than polynomial, but this is still way faster than n cubed over, let's say, log to the 1000. So asymptotically this is way better. So it's actually faster than any like improvement by polylog factors, but not as good as improvement by polynomial factor. So like some like almost 10 years now, more than 10 years now. But the idea is really cool, but not that easy. Can have a look. Yeah. Okay. Anyway, I hope you see more clearly, like at least from today, that shortest path algorithm really is like a dynamic programming. I just present them in the same format as when I present dynamic programming algorithm. Okay. So there are 2 exercises I wanna put out. Okay. So this is a kind of interesting exercise, which is like suppose that you have computed all paired shortest path in the whole graph already. Like you have computed distance from S to T for all ST. Okay. To do that, you need to take n cubed time. Like we know this. But now suppose that just one single node appear. A new node X appears. It shows up to you. And also, okay, like you have this graph, right? And now a new node appears, and you like people tell you to like what is like edges incident to X, like the weight of edges incident to X. Okay. So basically, the length from everyone to X and from X to everyone is given to you. And the distance, now like once X appear, you can see that the distance can change. Like maybe from S to T, it used to like this used to be the shortest path. Now once X appears, then the shortest path is like go through this way. So the distance can totally change. Now my question is like, okay, can we recompute APSP, like all paired shortest path, when a new node appears in time that is faster than recomputing from scratch? From scratch, you would take n cubed time, right? But can we compute new distance in just n squared time? Yeah.
And this includes computing all paths to X and from X as well?
Yeah, right. So that's the goal. And so you see it's much better than recomputing from scratch. And that's expected because we just add one new node, just a single node. Okay. This is kind of really a topic of dynamic algorithms. Like when you have big input and then like your input changed by a bit, can we avoid computing everything from scratch, right? Okay. So this is a hint, and maybe, yeah. Tell me like how would you do it? How would you compute the new distance from x to v for all node v? Yeah. Any idea?
Well, when we were doing Floyd-Warshall before, we were at like each step we were kind of adding a new k, like a new intermediate node. So we could just treat x like the very last node in that cycle.
Yeah. Good. So this is the kind of this step. Basically, good. You said that, okay, you can think like everyone here is V and X is here, right? And we have two choices for every pair S and T. We have two choices. Either like a new shortest path go through X, or it go through the old vertices. Okay, that's good. So with this idea, you can write it down like this, where for everyone here, the distance, maybe I write it down here. Distance new from S to T is min of either distance old from S to T,
Wow.
or distance, now it need to be new, from S to X plus distance new from X to T. So this is this step, and we do this for all S and T. This is this step here. But you can see that in order to implement this step, we would need to know distance from X to T and distance from S to T. So this step, now you are done here, like you take n square. But how to compute each of them here in n square time? How do you that's the first step that I asked here.
Here's my class. Yeah.
The graph directed or not? Does that matter?
It's directed, let's say. So I claim that, okay, here's like there are two n many numbers you need to compute. I claim that each of them, you can compute it in n time, order n time, each of them.
So if we have on the old graph, we already have the answers for the distances between any two nodes, right?
Yeah.
So when we add x, let's say we're going from x to any new node. Can you just look at the closest node to x? Like look at like in this example, there's only one. X only goes one direction, but let's say it's like it goes
Sure.
m directions or whatever.
Yeah.
Can't you just find the shortest distance? Like take the old data plus the length of the shortest distances, right?
Yeah.
That only gives you up to n combinations because x can go to n possible nodes, right?
Good. Exactly. So basically, what you say is like, yeah, thanks, Blake. So you said that, okay, if you want to know like what's the distance from X to, let's say, some node V here, right? You know that this distance must go through one of the out neighbor of X. Like this shortest path must go through one of the out neighbor of X. And then once it goes to this node, maybe W, how do you go from W to V? It's just from the old distance, the old shortest path from W to V. So it means that I just write distance new from X to V really is minimum over all, like the next node W, and it's gonna be distance maybe I just write the length from x to w plus distance old from w to v.
Yeah.
So that's basically n operation to compute this guy. And there are n many numbers. Like the flip one is just symmetric. Yeah.
I think this was a homework question on 376, like two semesters ago.
Right. Yes, exactly. Yeah. It was I composed that actually. So, okay, so good. So you see like some idea like Floyd-Warshall lead you to like dynamic algorithm quite naturally. Yeah. Okay, good. Now, so this exercise I will let you think at home, but let me tell you what I want. Like suppose that I have computed the number, the distance for each node that we learned today, right? But like what we want really is a path from S to everyone. So maybe what I want is like actually a shortest path tree, like that is like that is a subgraph of G and it's a tree, and such that like the distance just by going through this tree is just the same as distance in the graph. Okay. So to compute the single source shortest path, you might take like MN if you use Bellman-Ford. Now I claim that given these numbers, the distances, you can compute this shortest path tree in just linear time, m time. How do you do that? Well, you can try to think about this.
M is the number of edges.
M is the number of edges. But the point is like given distances, you can really just extract the shortest path from it easily. So try to think about this at home. Okay. All right. So now we will talk about Dijkstra. And yeah, I'm gonna remind you again what Dijkstra is. We will actually, like in previous classes, maybe you didn't prove the correctness of Dijkstra, like formally. You have seen it makes sense. We will do that next class. But at least let me remind you what is Dijkstra and try to prove the correctness of that next time. Okay. So, okay. Dijkstra is what? Dijkstra is like, it's similar to breadth first search, really. But what breadth first search is, you think of, you have unweighted graph, like no weights, right? And you just start with like everyone on like the first, like everyone like incident to you. That's like kind of time one. And then go to the next time step. You go through everyone incident to your set. So that's second step. Okay. And the way one way to think about this is like to have like some continuous view, right? Like imagine that you kind of pump water from the source, and the water kind of keeps spreading, right? So it starts at time 0, and when water reach node T, then you check the time, like the time that like it reached this node, it's gonna be distance. It's this distance. Like you pump the water from here, and once it's reached this guy, that takes like 1 second. Once it's reached this guy, it's just gonna take 2 seconds because each edge like can take 1 second for water to go through. Okay. So you can think of this continuous process, and what BFS is doing is kind of just try to implement this, try to discretize this continuous process so that you can implement it in computer, right? And the same idea works in weighted graph, and that is exactly what Dijkstra is, right? So like just imagine that, okay, if the graph now is weighted, you spend 1 unit of time, 1 second, and the water reach this guy. but the water would just reach like half of this. Take another second. Now it's gonna reach this guy, and the water kind of go through this half of this, and just this much, and so on. It keep going, right? And like what Dijkstra tried to do is to try to discretize this process. Okay. So, and like the pseudocode that you can like that describe what Dijkstra is doing is like this, like okay, like start initialize the distance at s to be 0, and everything else for now is infinite. Okay, and like there is a finalized set. Okay, so the finalized set is exactly like the set of nodes such that the water have already reached. Once the water reached some node, then that node distance, the distance of that node is kind of finalized. Okay. The guy that is finalized, its distance is no longer changed, and for other nodes, the distance can still decrease. Like we start from like infinite, and the distance can keep decreasing. Okay, so now okay. Suppose that we try to discretize this continuous process here. So suppose that like I set the red edges to be like the edge used to deliver water to a node, like this one. This is the red one, and the blue one is just an edge that might have water flow in it. So the blue one here. Okay, and basically it's like this guy is like a finalized, and out of this guy are the one that are candidate to be finalized. So you can ask yourself like the question, how if we want to discretize this process, we just need to ask like who is the next guy to be finalized among the node incident to blue edges. Who is the next guy to that the distance is finalized? Okay. So what would be like the next node in this case?
It'd just be B.
It's going to be B. Basically, it's the one that is kind of closest to this set. Okay. Like it's just the one with shortest distance to S along red and blue edges. Okay, because the water can kind of go through we know that for now the water can only go through red and blue edges. And we just need to check who is like the shortest guy that use only red and blue edges. Okay. And once you know that B is the next guy, then you put B here, and B will be put in the finalized set, right? And then you kind of continue like the set, like continue updating the blue set. Okay. All right, and okay. So this physical intuition that you can finalize the distance of some node here really works because there is no negative edge. Okay. Can you like give me example if we allow negative edge? What would be like the scenario that we cannot really finalize B?
So maybe if like on one of the fives there was a negative 100 that went to B, then the shortest path from S to B would be to go through that negative 100 instead of to go through the 2 here.
So you said like maybe this one have negative 100.
Yeah.
which this one, right?
Yeah, well, I was thinking like on one of the fives or something.
On-
It doesn't really matter.
I
Like,
see.
One of the nodes that.
I see.
But it doesn't
like,
really
like
matter.
here, yeah.
Won't those be too close? Like, oh, you mean on the fives? Never mind. Not for me. Okay.
Right. So yeah, anyone really, yeah. Okay. Yeah. So it like this one is already kind of finalized and say that the distance is 2, but at some point you have like a shorter path and it cannot be finalized. And because like there is no like a negative length in real life, right? So that's why like this intuition of water flowing doesn't work in when we have negative length. But like with positive length, then you see that like the finalized set is kind of monotonically growing. Yeah, anyone that we have finalized will be finalized. That's the case for when the graph have no negative length. Okay. And this is kind of okay. So what you do is just repeat until every node is finalized. Basically, find the one that is not finalized that has minimum distance that use only like a blue and red edges. Okay. And this is like basic. What this distance is basically will be the distance using only red and blue edges. Like we maintain some distance here. Okay, and this will be keep updating. And how do we update? We update using this rule. Okay. I will go into this more in details, like and prove it formally next time. But for today, I wanna end with some digression. So, okay, Dijkstra obviously is really famous. He's like really like influential figure. But like not just because of the Dijkstra algorithm, but one of his famous quote is this. Right? He said like, computer science is no more about computer than astronomy is about telescopes. And I really agree with this, especially like if this is like a theoretical computer science, because when you kind of ask yourself, what is computation, right? So one of the like a big figure in TCS, R.V. Wigderson, like he tried to define computation, and what he said is that computation is really just evolution process of some environment by a sequence of simple and local steps. So that's the case for computer. Like you have an algorithm, the process that like computer is just like the environment is just a sequence of bit string, right? And you keep updating using some local step. Like you think of Turing machine, for example. The configuration of Turing machine is updated using some simple and local step. And this is true in computer as well. But this is true in many other settings, right? Example of this object that evolved in the environment can be bits in computer, can be computer itself in the network graph, and it can be protein in cell, it can be cell in the tissue, it can be neuron in the brain, and so on. So my point is that computation really like is a theory that really encompasses and can model so many levels of whatever we care about. So yeah, theory of computation have something to do with all these things, and hopefully I talk about like a distributed network at some point, maybe in like a next few class. But yeah, so what we're gonna do next time is to give a formal proof of Dijkstra, and yeah, look at dynamic shortest path. Yeah. Okay, see you next time.